now we have a third solution. Someone else, another scientist, say, no, I will not follow these two algorithms. I have another idea. So what's his idea is actually, this is the bubble sort algorithm. And why it's called bubble? It's like we will start from the end, not from the beginning. Catch the element at the end of the array, okay, and just step back. If a smallest element, okay, if the one that I'm catching is smaller than the elements that I have, then actually this is like a bubble, okay, coming out. Then we do this one, okay, and we keep actually compare that element. So imagine that I have one here, so that's my array, and I have one at the end, and all numbers here are actually smaller than 1. Okay? We have, for example, 7, we have 10, we have 9, we have, I don't know, 3, and we have 2. So when I compare 1 with 7, yeah, 1 is smaller to the swap. Compare 1 now, because 1, 7 come here, and then 1 here. Okay? Compare 1 with 10 to the swap. So we have 10 here, 1 here. Compare 1 with 9. And so on until we have actually 1 here. So what we will have then, 9 is here, 3 will be moved here, 2 will be moved here, and then we have 1 at the end. Okay, good. Is it sorted? No. This is the first pass. Now the next pass is actually, you will go again, okay, take the element, okay, the next element, and you try to compare, okay, with the next. So, in each iteration, we have two things. We have I and we have J. Good. I is for the number of passes that you want to do through whole, from here to here, all passes, not the number of comparison, okay? It's all passes. So for example, with 1 is the first pass, then with 7 I will do again the same, this will be the second pass, and so on. And then we have J. J is the number, it's actually the pointer to the index of this position and comparison. So for example, J always go from N, and you actually subtract until again I. So I is actually used for two things. The number of passes, and so I the first time was actually 1 if we actually index from 1. Then the next time I will be actually based on the algorithm will be 2. So this means that I will go down with J and compare here, but not will compare with this one the next time. The first time I will compare because I is actually initially 1, but the next time I will not compare with I. So for that we have a reason. You know what's the reason. Come on, guys. It's really simple. So because we actually put the smallest already in the first index. So the next time there is no need to compare with it. Okay, so I took it from here and I compare with all numbers until I reach the end here. So I put it here, 1. So next time I have 7. I will compare with 10, swap, then with 9. Okay, suppose that here I have 13 and 12. I will compare with 13. I will compare with 12, but I will not compare with 1. Because it's the smallest. We already compare this number with all numbers now. And then the third pass, I will become 3. This means that I will not compare with the 3 and the position below it. Okay, because this part is already sorted now. So this is the way how it works. And here the algorithm, as said, we have I start from 1 to n minus 1. Okay, these are number of passes. And we have J is actually from n down to I plus 1. This is what we have explained just now. Okay. Every time we compare if J is actually less than J minus 1, as we did. If it's the case, we do the exchange. And the time complexity for this algorithm is n to the power of 2. look at it, two nested for loops or two nested loops, both of them actually n times. It's n times n. This is another example here. But I want from you to focus on one thing in this example. Here is the array. This is the initially we have 5 elements in this array. And in pass number 1, we will say that I is 1. So this is the first pass. J is actually at position 5, right? Because we start from n down to 1. Okay, to I. This is the algorithm back, just to remember. J will start from n down to I plus 1, right? This is what we have identified. Okay, let's catch now n is actually 5, which is now j, right? J is equal to 5. We have the value stored at 5, 1. We will compare with 4. We have the condition is true. Aj is less than j minus 1. We actually exchange the data. Then we compare 1 with 3. Yeah, it's smaller. Then 1 with 2, it's smaller. Then 1 with 5, it's smaller. Then this is the first pass. We have 1 at the first position. Okay. Now, is it sorted? If you look to the first pass, to the end of the first pass here, it's not sorted yet. Okay. This is why now we have the second pass. In the second pass, we will have 8 first and compared with the 3, but no, it's not less than. Therefore, okay, there is no exchange. 8 is actually, I will do it, okay, but there will be no exchange anymore. So we'll keep it here, then we'll go now with j actually with 3. Okay. Now, this is, I mean, you can look to the algorithm. We will update because n will start, we are still in the same path. N will start, j will start from n down to I plus 1. We will try the first here condition, it's not working out, then I move j to here. We compare 3 with 2, okay? It's not less than, okay? Then this is the second pass, we keep it as is, okay? Sorry, we have 2 here. You move to 2. 2 you compare it with 5, you do the exchange, and this is the result of the second pass. Now, look to the data here. 1, 2, 5, 3, 8. Okay, good. Still, we have some numbers not ordered here. This is the third pass. 3 with 5, and we do the exchange. Of course, this is just show the number of exchanges, not the tries. Because in some tries, there is no exchange. I'm not showing this here. Okay, good. Go back to the algorithm and look to I, how we define I. We said I will go to n minus 1. Okay? 4 times in this case, because here we have 5 elements, minus 1. It's actually 4 passes. Okay, this is the third pass. My array is already sorted in the third pass, but the algorithm will try the fourth pass. And this is actually a problem because we are doing more effort than needed in the current algorithm. Okay, this is our algorithm. And we have explained actually this question why actually we go to I plus 1. We have answered this. Now the next question, and this is the answer here. But what is the problem of this algorithm? I have already explained it, but I want from you to suggest a solution for it. So the problem of this algorithm that the one that we have here, I will continue actually do passes check, okay? But at some point maybe the array is already sorted, okay? So why I have to continue to? So for example, imagine that I have 100 element in the array, and the first pass all actually like, I don't know, I have write something. It's like this. This is my example. 100 element, you can imagine whatever, or 1000 element. Here we have 1, but all the other is actually already sorted. Like for example, we have 100, 99, etc., etc. Then what I will do, just move this with the first pass, move, move, move. Then I have one here, two already here. Then we will have the 100 already here, 99 already here. Okay? 8, 7, and it's sorted. But the algorithm will actually do n minus 1 passes. This means like 99 passes. Okay? We already tried one. Then the rest is 98 remaining passes, and it's already sorted, but it will actually try this out. This is like effort, right? There is no need to do that. The question now, how we can actually just only try with looking to this algorithm, fix it a little bit, add something where we can stop this from happening. Yeah?
We can, for example, add
So instead of
something like
taking the
flag,
number
which is
directly
telling
somewhere
the
that
exchange
it's
and
supposed to
value, and
do
that
this,
flag can
you know,
restart
Yes.
subtract, and then
Exactly. So
it
what
gets
we
the
need to do
right
that
place, is that what it means?
in the next check, if we are doing no exchange, okay, so we tried this, we did a lot of exchange the first time, we finished from the first pass, let's take the next one. Then the remaining is 97, we try with the next one. In the next one, if I did no exchange, this means that my data is sorted, therefore drop all these 97. Okay? Simply you need a flag, okay? So this is updated, we call it swap, and it's initially false. It is the same algorithm, exactly the same algorithm. I just only add something here between these two for loops. It's called swap, and it's initially false. It's a Boolean kind of data, okay, a variable. And inside the for statement, the next for statement, after the exchange, if you actually perform this exchange, change swap to true. Good. Now, after the for loop, so this is the number of passes. If you did a pass and you perform this for loop and no exchange happened, then break. Okay? So you are out of all passes. This means that your data is already sorted and you don't need to go forward. Okay. Okay. Some kind of things. This example could happen in the exam, like not the same one, but this is what I told you, that you don't need to remember the algorithm. If there is something, this kind of an example that I can give you an algorithm and ask you to update it to fix something that happened there, that could be one of the opening questions for it. Okay. So far, so good with the bubble sort. I'm not really sure, but I think I'm going fast with this lecture than usual, right?
Yeah, I'm surprised. It's almost there.
See if there is.
And we're already here.
Now, we have the so-called shell sort, and it's again for applying the same problem, but different way of thinking. You remember the insertion sort? The first algorithm that we have done? We have some cards, and we just imagine that we have nothing here on the left hand, bring the first one, put it sorted, then the next coming, we try to find the correct position for it and put it there. And these are the sorted part, this is all unsorted, then the next is coming and try to find the right position for it, and so on and so forth. That was the insertion sort. Now the shell sort is somehow an optimization for that insertion sort. Okay? It will try to decrease the number of comparison, okay, by chance. Okay, how we do that? So this is some theory part here about it. Again, shell sort is a generalization of insertion sort. It tries to improve the efficiency by reducing the number of comparison and checks needed. That's good. How we can do that? Okay, and the bad news is that it's actually sometimes it's the idea was actually to reduce the number of comparisons. This should actually reduce also the number or the complexity of the algorithm. Then why we end up with n to the power of 2 again with the shell sort. We will explain that, but it will be better, okay, if by chance, okay, the data and was actually the input in your array somehow fit, okay, the shifts that you are doing, then you may end up with this number of comparisons. But in general, it's actually n to the power of 2, and we will explain why step by step. So the idea is that you have an array, okay? You need to find a gap. Instead of like getting one by one, so this is here where I want to sort, and this is my data. I get this, put it here because we don't have data. Then the next one is coming, I need to compare, right? And put it in the right position, and so on and so forth. So instead of doing this, we will do like a gap. I will take the first one, right? Okay, I have it here. Then the next one that will come, not necessary to be I plus 1, okay? I is now the part sorted. I plus 1, that was the insertion sort algorithm. Now I will not look to the next, I will do a shift, okay? I will compare 2 position forward or 3 position, we will decide about that, okay? You will say, okay, I will look 4 position forward and get the number at index number 4, for example, and now compare it, okay? So now the comparison is not like going with the adjacent one by one. You will do jumps, okay? And you compare. If it's this, you will check. And if it's y like, you jump it twice, okay? Like, think about the following example. Imagine that your data is like this. You have 5 here. And let's say, for example, I have, I don't know, 4 here. And we have 1, or let's say, let's make it simple, 3. And we have here 2. Okay. Just to simplify the things. Instead of say, okay, this is 4 now, the next is 3, compare with 4, change. Then the next is 2, compare with this and this, change. Okay. Then it will be sorted, right? Because 2 will be the right position and 4 will be the right position. With the shell sort, if you say by luck, you don't know how the data look like, you say I will do H as a jump, the gap, I will do it 2 positions. Okay, this means like this is I plus 2, for example. Then this is my number. The next that I will compare with it is not 3, it's 2. Because you will jump 2 positions forward. And 2 is less than 4, you do the exchange. This is 2 and this is 4. And so, okay? So the idea is that you will do jumps for the sorting, not one by one, to actually minimize the number of comparisons that you are doing. But this is actually depends on luck. Because if you don't know the distribution of your data, how they are distributed, and now we are talking about statistics, but we'll not go deep down there. If you don't know the distribution or the population, how your data actually formulated or come from or look like, you would do this by random. If I ask you how you want to specify the gap, you will say 4, maybe 8. Depends on how large or the size of your data set, right? So for example, if I'm expecting 100 elements, maybe I will say, okay, I will do a gap like 16. Okay, good. But then it might be it's not the case, okay? So maybe here I have 1, and here I have 0, okay? So let's just write it down here. So this is 1, and this is 0. So yes, the first time I did just one comparison, but look, it's still not sorted, and I have to do more jobs. So then it's actually depends either on if you know already how your data is actually look like. If you know that, you can put the gap in a way that works good for you. Okay? But if you don't know, maybe you decide it, but it will not work good for you at the end of the day. Therefore, the worst case complexity how this algorithm works. We have 8 positions from 0 to 7, and h, we decided using a formula. Usually we will do it n by 2. This is the most used way to decide about the gap. So if you are wondering whether to put the gap, the jump 2 or 3 or 4, how you decide about it, usually you will do it n by 2. And we do more than one pass. The first pass is here, will be 4 position. Okay? The next pass will be 4 by 2. So it will be 2. And so on. Until the gap will be 1. Okay? So it's not just only like now, we will calculate the pass, it's actually 4. Okay? Let's do it together. This means that from 0 to 3, the first 4 position will be the subgroup. The next subgroup is from 4 to 7. Okay? How will we do that? Initially, we are on I, it's actually 35. Now, I will compare, but with what? So, what I have on the left-hand side is subgroup number 1. This is what I have on the left hand. This is all in the right hand. Okay, in another word, this is the cards that I have on my left hand, like what we have learned about insertion sort. And these are the cards on the table, and I don't know what they are containing. Okay, now, before, I was getting this one and compare with 10, with 42, and try to put it in the right position, but now no. I will actually look at 35 and compare with 40 after 4 positions. Okay? From 0, the next will be actually at position number 14 because it is actually 0 plus 1 plus 4 because h is actually 4. This is the jump. Then I compare 35 with 14. If 14 is less than 35, you do actually the swap. Okay? You exchange both of them. Therefore, okay, this is will be exchanged. 33 will be exchanged with 19. 42 will be exchanged with 27. 10 will be exchanged with 44. Now this is the new array that we have. Okay? This is how it will look like. Now my question to you, is it finished? Are we already sorted? Still not. Then this is the first pass. The next pass is actually h divided by 2. H is now 4. Now the next time it's 2. Okay? We will keep reduce the gap until it's 1. Okay, then this is the next pass. We will have every 2 position a subgroup. Now 14 I will compare with 27. If it's less than, we will do the exchange. In this case it's not. Then 19 we will actually with 10. 10 is less than 19. We will do the swap. Next, you have 27 with 35. We will not do any kind of exchange. Here we will have 19 because we already swapped them. Okay, we will have 19 with 33, no change. 35 with 42, no change. 33 with 44, no change. Okay, then this is our new array. Okay, and the question is it sorted? Not yet. We will have also to divide now h by 2 again. Then 2 by 2, it's actually 1. When it's 1, it is actually simply insertion sort, like the algorithm that we learned at the beginning. When it's 1, it is like the insertion sort. We are here, okay, at position number 1, you compare with 14, because we will consider that this is the first position, is the sorted one on the left hand, and all things here is not sorted, right? At 10, we do this one. Now next, we will consider that these are sorted, okay, and we look to 2, but there were no exchange in this one, and we do the exchanges and until it's sorted. So the third or the last time, you will do n times of comparison again. It's like the insertion sort, okay? So, as we have the example, the subarrays that the shell sort operates on are initially short, okay, because we have some jump. Later they are sometimes longer, but mostly ordered. This is the first thing that you can actually notice if you look to the example. But the shell sort is unstable, meaning it does not guarantee that relative order of equal elements will be preserved. Now, the last or the question for you, and I think this will be maybe the last part of this lecture, we need to think about it. What do you expect that the worst case of time complexity will be for this network? We have already clarified that it's actually big. O of n to the power of 2, but my question, why? How we come to that? What we have here, what we tried out, and if you remember from the complexity lecture, when you divide the problem into halves, okay, and you try to minimize the number of comparisons, you should end up with a better complexity. But this happens for several reasons. Okay, but let's go step by step. And here I'm not showing the shell sort algorithm for you because it's actually on the exercises. You will have a question to implement the shell sort algorithm. Therefore, I did not show how it works in terms of algorithmic, but you will do it in the exercise. You will get the algorithm and you try to implement it. Okay, first, we need to identify number of passes, right? And this actually is n divided by 2. And if you calculate the number of passes, if you remember, when we talked about the logarithmic, we said that logs to the base of 2 gives you the result of how many times I can divide n by 2, right? This is what we have explained. Then, this is the gap. How many times I can specify a gap? So we start by 8, then 4, then 2, then 1, okay? So then it's actually log n. Log n is the number of passes that I need to perform based on the gap. Okay, good. This is log n. We have nice thing. Log n is the smallest, or in terms of complexity, it's the lowest thing that I can get. And it's the best thing actually. If I'm getting something that can work for me, log n, then it's better. Okay? But still, there are other calculations. This is just only the number of passes. The number of passes is actually log n. But every time, the total cost is actually n for each pass. Why? Go back to the example. This is the first two subgroups. You compare this with this, this with this, this with this, this with this. You can say n times for the first pass. This was the first pass. Then the next pass. Okay? Again, you compare all elements. So for each pass, you do n times of work. Okay? So then it becomes actually n log n. Good? Are we done? No. The last pass, when h equal to 1, is an insertion sort algorithm. You will need to go through all n's that you have, element by element, one by one, and compare that with all elements that you have there. This will be, if you remember here, this is the last pass. I consider 14 as sorted. Then I get 1, compare with 14. Okay, we have it here. Now we will take 27 and compare it with these two. Then you will get 19 and compare it with these three. You will get 35 and compare it with the other, and so on and so forth. So you go n times with n times of comparison. This is n to the power of 2, like the sorted algorithm. Then the total will be n times log n plus n to the power of 2n. If you remember from the first lecture or the second lecture, we have a formula says that if we have something looks like this, then we will take the largest. If we have two things that sum to each other, we will look to the largest one. Because n to the power of 2 will dominate the results. If you try to draw this one, you will find that it will take the the shape of n to the power of 2, like this, okay? It's not n of n. Therefore, we drop the smallest. But the actual result, it's n, look, n plus n to the power of 2. This is the actual in the worst case. But usually we try to approximate it, so it is n to the power of 2. Okay. In the best case, no, it could be n log n. When you have maybe data is almost sorted, and what this means, that we have less number of inversions. You remember the inversion in the first lecture? We talked about inversions, how to calculate the number of inversions, and we say that if we have too much inversions, this means that the more work that you want to do to sort your data. Okay, I think this is what I have for this lecture. Okay. We have more algorithms, and I could actually add some more of them here, but I just don't want to confuse you with many algorithms in the same. Now, my question to you, do you have any question? Do you have any doubts about any of the algorithms that we learned today? Okay, now my question to you, can you come out with a better algorithm? Or maybe another idea. We have learned about four kind of sorting algorithms. Do you have something in mind where you could do better? Not in terms of complexity, but another idea to sort the data. Now maybe you can write it down. Just try it now as simply quiz for 5 minutes. Just write it on a paper, sheet of paper yourself if you have. And then you're welcome to present it.
Go on, write it. I'll be supporting you.
Okay, I will give you 5 minutes. Just think about it. Please don't use the internet.
Try to think about how do you sort stuff in real life. Maybe say like the cards. I usually And twice. Yes, please. Please come here and you can use the chalkboard.
So my idea is if we split the array in half and then we just compare halves to each other and check if it's sorted out.
Did you try it with an example? So okay, that's good. You tried with two halves, but what you want to swap as the pairs with the last? Okay.
Yes.
Yeah.
Then I check if this is sorted, and then I
Okay.
check if this is
Okay.
sorted.
And what would be if you tried with an example? So suppose I don't know, I don't have an example with mine, but if you tried with something that would this bass be enough for sort or you need more basses?
So first I need to
So just let me write some numbers. I need just so for example, let's assume that I have 10, I have 8, and I have 7, and I have 1, 2, 3. Okay. So the first time you compare 1 with 10. Okay. Now, no, I should actually.
because it's already sorted.
Let's already sort, but let's assume that I want to sort it in descending order. Okay. So 10 with 1, I need to swap it. Okay.
Yeah.
Okay. Then 10 is here, 1 is here. Then actually 2 with 8, then we will have 2, and we have 8, and then we have 7, and we have 3, right? Okay. What's the next? It's already sorted now. This example, we need 1 bass. Okay. But you have some examples where maybe you write this as an algorithm. You have just put random examples.
You can't tell if that's a 4 or a 1. Oh, never mind.
And then I need also insertion.
Yeah, the second block looks like a 4 and also like a 1.
Here is no swap.
Here's no swap.
1 with 4 is no swap.
Yeah.
Good. Then it's again doing this work here with this example. We don't need, I mean, now my question to you, what if I have, you need to try this with some data, but you need to write it as an algorithm and see that how many passes you need at that. The question is, what if I have, this is an even number of positions, right, that you can divide by 2. You have 6 positions, so you have 3 on the right and 3 on the left. What if I have 7 positions? So there will be no one exactly. So I will have, for example, here one something more, and
Is this
here we will
literally
have
the
maybe
finish of the
0.
basic?
So the question, where
Only
it
need
is
for
my
2
mid.
hours? Basically.
Okay, then this is the mid, but this will be compared with 0 or with 10. So before you say, okay, this is now, but we have this as a mid. So we would compare 8 with 0, 1 with 10, 5 with 4, but what about 2? Then maybe you need to look at 2 as a mid pivot and compare with the I plus 1, I minus 1. If it's larger, okay, then you look to this side.
Okay.
So then you have 2, maybe you compare with this and this and this, if it's actually this and this one. Okay? Not necessarily not this one. So because now we have 8 and 0, then we bring 0 here and 8 here, right? I will just work with the same.
Yeah.
it's already sorted. You have 5 and 4, we have to switch. We have 5 here and 4 here, right? Now we have 2. You look here, and here it's the same. It's less than the 5, and it's also the same time less than the 4. Then you actually need to take this one and compare with from here to the end and find the right position for it. But I think in terms of complexity, this will take n to the power of 2. I'm not really sure, but you have to write this as an algorithm. So I don't know how many passes you need. So if we need one pass with this comparison, then we have n comparison, then we will actually have big O(n). But I'm not really sure about number of passes here. How many times I need to divide this? Because for example, here it's not sorted yet also. Then you also need to divide this and actually compare, for example. So this means that maybe I need n times n. Okay, and this is n to the power of 2. But yeah, good. I mean, this is also a new way of thinking. Okay, like the other one they did, it's a new way, but end up with the same complexity. Any other way to show? Yeah, please. From both of you. So.
I mean, mine is just oversorted.
Yeah, that's fine. Come, please. We have 2 boards. Each of you can start writing, and then you can actually one by one start something. Anybody want? We'll write maybe an example first to explain to the people. Then maybe you can write your secret. You can make the writing a bit darker so people in the back can see. But yeah, continue, please.
I mean, I can already explain. So, I mean, my idea is like. I mean, I can just speak loud. That's fine.
Okay, then speak a little bit louder.
Yeah. I mean, my idea is like literally not even unique. Like we just had it before in class. It's just Bogo sort. So Bogo sort just means you take the algorithm, take the array, and you just like randomly arrange the numbers and hope that it's basically sorted. And you do that like until like you resort it, check if it's correct, you resort it again, and so on.
Okay, so it's like like the shell sort algorithm. The shell sort algorithm, they have this gap, okay, and they compare based on the gap. Randomly, they chose the gap. For example, starting by 4, and then they start. Hopefully, after we minimize to 1, it's sorted. If it's not, I need to perform the insertion sort again and again. But yeah, I would say, I mean, just use a random. How many? I don't know. In terms of possibilities, I'm not really very good in that. How many? What are the possibilities that I could have to do randomly that I have the array is sorted here? We have 1, 2, 3, 4, 5, 6 position. Okay. So each element actually could placed at least 6 positions.
Yeah,
And also in random, you not eliminate redundancy because you could actually do random rearrangement, but you end up with a solution that you already performed before, and it's not solved. Oh, it's a way to do that, but I think you will end up with, I don't know, maybe in terms of complexity, so it's very large number because you will do this by luck several times. There is no control.
wait, sorry, what does it say?
It's the factorial of it.
Oh,
This is it's a huge number. I'm not really sure, and maybe it will be greater. Why? Because it's a good idea, okay, to start randomly, just okay. Maybe the next time when I try to order this, I will have
randomly sorted.
1, 2, for example, let's say 2 here is and 1 is here. By randomly just do that. Okay. And then I try it again. Okay, then I have 1 here and 2 here again. So there is a repetition that you can't control in this way.
Oh, I guess so you could like kind of adopt the algorithm in a way where like you
And this
know,
you can,
like you store the states that you
yes,
previously
you
had.
can do that by saying, okay, I will do the exchange, for example, randomly. Okay, the first time I will change 2 position forward, like the shell sort. Say this and this and this, for example. And then you do that and you store that you actually selected 2 as a jump. Then the next time you try any random number, okay, but not 2.
I meant it more like as in you just save the
Yes,
entire.
but without I save
could
this
I
thing, I can save this thing that I use.
No, what I meant is
Yes, I know, but that will be difficult because if you want to take an image for the array and you need to compare it with another array that is not the same.
What do you mean it's not the same?
So, this is the state of my array.
Right.
Okay, I will start something.
Right.
Then I have, this is my actual array. What's the state of the array? How do you want to decide about the state of the array? This is my array. I want to store the state of it. What's the state?
Almost sorted.
I mean, you have almost sorted, but what does it mean? Where is the elements that are not sorted? So I will give you an example. So here, if I have this one, 1, 2, and then I have 4, and let's say we have 0, and we have 5. This is almost sorted, right? Because we have just only one element that is not sorted. The other are already sorted, almost, right?
Right.
But I mean, in terms of number of tries randomly, okay? How many tries I can do this randomly? Okay, we're dealing with algorithms, not our eyes. We know that we just need one to do that, okay, right? Me and you, we know from just talking to the array, but the algorithm does not know things. The algorithm needs to start here and do swapping and do comparison, right? By random, how many tries I need to put 0 in the right place now? Just random. No idea, right? This is what I'm trying to tell you. So because it's actually too much tries. You can actually first try 0 with 4, 0 with 2, 0 with 1. These are all tries. And there is a repetition also. How we can eliminate the repetition? So if I change 0 with 4 the next time, 0 here and 4 here, that is the next random. How I can actually make sure that I would not actually do this again, 0 and 4 again. You need to store this somewhere. So this means that I need to store the whole data as the way they are sorted, like an image for it. And the next time that I put in the same image, compare, no, this I tried before, this step. Or the best way is like, why I'm not just doing these jumps, like in the shell sort. Say, okay, I will choose this number randomly, like not in the shell sort. In the shell sort, we have the size of the array divided by 2. Now I will just choose random. Next time I will not try this number. Okay? Maybe by that you will get the data sort. But yeah, it's also another way of thinking, but not the best way. Okay, what do we have here? And fortunately it's not working, or I don't know, or I'm not really sure how to do it.
I was trying to reference.
No, it's not very much.
Okay. So I was trying to make something like modified insertion sorting, but instead of checking by one if the number is higher or lower, like it, instead of checking one by one if the number is lower, I decided to check from the middle of it. And if, because like we know that, for example, here is already sorted. Let's assume that we are in the middle of insertion sort here, and like we are getting the table, so like the left side is already sorted. So when we are checking the next element, we doesn't have to go step by step. We can check by the middle. If it's, for example, here with 8, let's assume that it was filled by 2, and we see that 5 is lower than 8. So then we can just check if in the middle of that left side of the A, if it's again smaller or higher by the middle number, and just insert it and so on. Then 7 and try to put it in the middle. Then we just have to move every time the table, but I think it can be a little faster.
So, do you understand what she's saying? She actually has a nice idea, like the insertion sort. So you try with the insertion sort, okay? This is the unsorted one, then you get the next, you try to sort it, okay? After some steps, okay, you stop doing this every time. So the next time that I have 5 is coming, and this is my sorted part, there is no need to compare with 10 and 8 to find the right position in 4. Next time what we do, split this to 2 parts, compare with 4 and compare with 8 directly, okay, to the right, to the middle, okay? If it's actually less than 8, then maybe you can compare with this part. If it's actually greater than 8, you go to the right part, okay? So, which is a nice idea, okay? Then try with all numbers less than at this position. And this actually makes sense if you have really a huge array, so thousands of numbers in an array, and you will save time. But in terms of complexity, how does your algorithm look like here?
So I didn't finish it fully because I didn't write the moment when we are saving the data to
Yeah, but does not make, it will be inside. You will have for loop to end, and you have while loop that actually
go just until E by 2.
I by 2. I'm not really sure about it. You have, you need to try it out and make sure try the i's out. So you divide I by 2. You have to check that out if it's correct. But let's assume that this is correct.
Here will be one more step to check if that's, like for example that 5, if it's smaller than I by 2 or higher than I by 2.
But this is a if statement, right? It's an if check, right?
Yeah.
But it's not a while loop. So we have a while loop and for loop here. This is to n. And this is actually n by 2. Okay. That could actually do n log n.
I hope it will be n log n,
But
I'm not sure, and counting that we have every time moved the whole
yes.
array to
Yeah,
the right,
this is.
cannot be fast.
But this is if it's inside. If it's a one step here. Okay. Could you please, try? I mean, it's really nice idea. I like it. So maybe you can try to next time bring it on the correct algorithm as a whole, and maybe you try out to calculate the complexity of it and show us actually with a nice example. Maybe you can prepare a slide, you can present something.
I will check if it's working.
Good. I mean, when you check viewer, you find that we have a good student here that can bring actually solutions. Thinking out of the box is always nice. Good. Yeah. I think I want to present you something. I will stop here. Do we have other people who would like to try? If some of you already started initial ideas and they want to show these ideas, maybe you can write it by email if you are shy to come here. But also you can actually bring it to the next lecture. At the beginning of the lecture, say that I tried out differently and I have to. Okay, good. One more thing that I want to just tell you is about the exam, and I will make these guidelines available for you soon. Working now. Have it shared. Okay, so these are some instruction and guidelines for the exam. This is from the last year. I have to check it again if there is some updates needed, but this is actually the general one. Once it's available, it's there, and then will be the official one that I have. Okay, so this is a draft version. I told you at the beginning of this lecture that we will have 25 multiple choice questions and 4 open questions. This means in total that we have 29 questions. Okay. The multiple choice each with 2 points. So we will actually, I will use first grade from 100 point, and then I will actually change this to the 7 scale system. The open questions will actually take like 10 to 15, some of them 15 points, some of them 10 points. The open question is not just only to give an answer, there are steps that you need to perform or subtasks. So for example, question number 28 is an open question, but it maybe has some subtasks. And this is why I will divide the 15 points not in one task, it will be actually divided on subtasks. So this means that if you actually tried that open position, you did the first subtask, the second, and you failed in the third, maybe you will get 10 out of 15. So that's the way that it will. Okay, good. No aids are allowed in the exam, except I wrote for the administration that you can use Word or text editors, okay, to draft your answer if you want before actually. Especially for the multiple choice, sometimes you need to do a calculation. Okay? So maybe you need to write down something to memorize, for example. I don't know. Maybe you need to calculate the complexity of this one, and you need to write somewhere to keep track of thinking. Okay? Therefore, you may be allowed to use Word. Not bad, whatever, but not other tools, not other textbooks.
Are we allowed then to use paper and pen? When we can use Word, can we also use normal paper?
Yes, this is initial. Maybe I can also mention that. I did not mention that in my email, but that's good point. You can also do it. Yeah. But I'm not really sure how they strict with also this. I have to discuss it with them. Okay. What we have here. For the programming questions, you may write the answer using pseudocode or any programming language that you know. So if you know Java and you are good Java, you can write in Java. If you know Python, good Python, you can write in Python. If you are not good in both, you need to write a pseudocode, just write in pseudocode. Okay, that's what we learn. The use of existing libraries is not allowed. So what does it mean? So some programming languages provide already Java, they maybe have already a library that actually given an data, array of data, just call that library and it will sort it for you. Okay? So when I ask you to do something, okay, you should actually write the algorithm yourself. Yeah, this is here an example of what you can expect for the open questions. I have to check it again. As I said, this is draft. So for example, the first question you can expect a question or recurve. Okay? And you have to write a recursive algorithm. The second question you may expect a binary array. I give you the binary array, how it's look like. You don't need to draw binary array. Okay? Because in its learning you will not be able to draw something. Okay? And you will be asked to solve some relevant task on that array. On that tree, sorry. For example, check if it's balanced or not balanced. We have learned about that. Okay. Find the position of inserting a new element there. Where is the position? You don't need actually to draw it again. Just tell me the position of this new insertion, where it should go. Something like that. Also about graph theory, we will learn about graphs in the upcoming lectures. Some graphs and some questions on the graphs. And also we'll be presented with a pseudocode, okay, and we'll be asked to update it to handle a specific issue. Okay. That's some kind of how the open questions will look like. Yeah, as I said in the beginning of the lecture, there is no need to memorize, for example, the exact code could be based in mind, like how, for example, in public soft works. You need to remember the method, okay? But you don't need to remember exactly the pseudocode in the textbook. If there is a need to show or a question on this pseudocode, it will be like I will present the pseudocode for you and will be asked to perform some tasks. Any question? Okay, good. I think I will stop here and I will update this draft and make it available for you. And soon we will also, or not really soon, but maybe by the end or the last lecture, we will make, with the help of EAs, a demo exam for you, okay, with some multiple choice questions, some open questions for you to try it out. Okay. Good. Thank you for your attention.